Welcome to stream number 37 of our series here where I'm programming a game live on Twitch for the NES. So, sorry about last Thursday, skipping an episode, but yeah, the allergies were pretty bad, and so I was all congested and having a hard time focusing. I was had a lot of sinus pressure, so it was difficult to do anything. Figured it was better for me to get some rest, and you didn't need to listen to me kind of sniffling through an episode here. So the time before that, we were working on getting the attributes loaded into the game for the level. If you remember, spent some time going through this code and kind of re-familiarizing ourselves with it, because it had been a while since I had looked at this and I had forgotten some of how it worked in terms of how it loaded the tiles in and how it managed the attributes. Well, it didn't actually manage the attributes, but it how it zeroed out the attributes and what we need to do to fix that, given that we changed our file format structure to include attribute information. So if you remember what we did, let me close this. What we did was we changed the file format. So before, it was an entire screen's worth of data and then individual rows following that, but with the sort of weird caveat that the first screen started the full screen of meta tiles, right? And then each row that we wrote, they were actually rows above the screen because we're scrolling up, and so it made more sense to traverse down the screen in this direction and just load the rows as we went up. So what we did was, this is the old format. So the new format, well, we had 1 byte here. That was the number of rows, the total rows for the map. So what we did was we changed it so we wrote one, that same byte for the number of rows, right? So we still have that. And then we have four arrays of 4, or one array of 16 if you want. These are our palettes for the level. Right now we are only supporting the 4, but we'll need to fix that, obviously, but we'll get to that hopefully soon. The next part we did was we took we have our 64 bytes. This is our attribute information for the attribute table that configures what palettes the tiles in the name table are using, and then the rest of it is the same. We have our one screen, and then we have our individual row one by one, right? And we may find that this is not a great way to do this, and we need to change things or optimize or compress it. But right now, this is a pretty straightforward way of storing this information. The problem now, though, is that if we look at the game when we're playing it, it looks okay, except now we have this attribute information is wrong here for these meta tiles, and it's because when we loaded the game initially, those meta tiles here across this strip of screen have a different setting than these gradient meta tiles. And so they're using the wrong palettes, right? So if we go to the name table view and to the hex editor, no, to the PPU viewer. Hold on a second. Oh, why is that still on? My computer should not be on right now. Sorry. I have a Mac Mini here that I use for doing music stuff, and apparently it was on because it was making all sorts of noise. Why is it still on? What's going on? There we go. All right. Sorry about that. So, oh yeah. So as I was saying, this first palette is fine for these meta tiles here with the gradients, but then the blue meta tiles are using this palette entry here, and so when we scroll up, what we find is once we hit the point where we've got the blue meta tile attribute entries for these gradient tiles, then we're getting the wrong color. So what we need to do, excuse me, I'm still not fully recovered here, so still some congestion and stuff. We're getting the wrong color. So what we need to be able to do is we need to be able to load the row and its attribute information. So this row here, and then the corresponding attributes that would properly configure the colors that we would display here, so that as we scroll through this screen, we actually get the right colors. Like, so this is the blue that we expect, but this is purple. Or actually, you know what, maybe this purple is, sorry, this purple is actually the right color if we go to the asset tool. Is it? Oh no, the blue is correct. The purple is as a result of the colors used by the gradient here. So anyway, the point is that there's a lot still to kind of get this going, and this is only with the 4 palettes. We need to be able to have a way of potentially swapping palettes, but let's get the data set up to load the attributes properly as we load the new rows, and then once we've got that, we can determine if we need to handle more than 4 palettes for these levels, because I mean between the 4 palettes you basically have 12 colors plus the background color that you can use if you don't do any swapping, and that's separate from the colors that you can use for the sprite. The sprite has its own set of potentially 4 different palettes of 3 colors plus the background. So we may be okay depending on how the game goes. What I want to do is I want to get this working enough that we can just move on, and then we can start doing stuff with the HUD, and then once we have that working, we can get into some level design, I think. Well, actually no, so we gotta do collision detection with the background, and then maybe we can start doing level design and figuring out what other enemies we want to have and that kind of stuff. So let's get the palette loading going properly, or the attribute loading going properly. And what I'm thinking is that we probably, let me close the asset tool here. Where is it? What I think we probably want to do No, not full screen it. What I'm thinking we probably want to do is alternate between the row and the attribute information. The reason being, I mean, that just is kind of a logical way to do it, right? You update the row and then you jump to the attribute information or the attribute location where you would write your new attribute info. So something like that, possibly. And we just kind of interleave that into the data of the map and then just keep swapping or keep reading row by row. I think that would work, and that's relatively straightforward, and it maps pretty easily to the 8x8. The only time, not 8x8, the 4x4 meta tiles, the only time we're going to have any sort of issue is we know that the screen is really only 8x7 meta tiles, not 8x8 meta tiles. And so the problem we have because of that is that the last row of meta tiles initially is actually truncated, which that's not a problem so much, but where it becomes a problem is as we're scrolling, we are going to hit a problem where the attributes are spread across two different sets of attributes, because the last set of attributes handles the two rows of 8x8 tiles which are present on the bottom of the screen, and then it doesn't handle anything related to the top of the screen. So those additional 2 bytes are actually, or they're not bytes. What are they? Right, they're not bytes. We've got 4 bits for, we've got 1 full byte. So that additional, for that byte, the additional 4 bits, the nibble is not actually used, because in order to set the other 2 rows of 8x8, we need to set the attribute for the top of the screen. So we're going to have to build some logic in the NES code to know how to do that, but that shouldn't be that hard because it should be a predictable address that we can track accordingly. So let's do this. Let's work with the attributes, and then we can. Why is this highlighting? Oh, because I typed an extra 4 there. Okay. Let's do this, and then let's get this data loaded, and then we can start working on the NES code to get the attributes changing properly. So let's see. For this part, we are mapping the attribute results into the 8x8 for the screen, which is actually too many. It should be just 56. We don't need 64. Why are we writing? Oh no, I'm sorry. We do need 64 because the attribute part of the screen is 64 bytes. So we're writing out the full 64 bytes. But we are doing that based on what we're saying. Okay, if the map palette for the palette doesn't equal the map, and the palette index is less than 4, so okay, so we're doing this for the entire screen here, and what we need to do here is we need to do this for the row, which is just 8 tiles, right? And then what it's doing is it's packing the palette index into 1 byte, because our meta tiles are currently using 1 palette for the 4x4 meta tile. Again, all of this kind of stuff might change as we work on the game and realize we want to do more complex stuff with the colors and the graphics. But for now, I want to get this sort of most simplistic way working so that we can start working on the actual game and not the tech behind the game. And then as we develop the game more, we'll be able to kind of work backwards and figure out how we need to change how the asset tool exports things, etc. So, like I was saying, for this, we say this is going to be start height times map width. We can never does what I want in C++. In C#, it's pretty smart, but that's all right. Int start location equals start height times map width. Oops. Yeah, I know. That's not okay. So this gives us start location. Start adder is less than start location plus 8. Right, so that's, we're going to take the current location, we're going to take all of the meta tiles in here, and we're going to, for each of them, write a single byte based on the palette index that the attribute that the meta tile uses. So we have this map palette. So let me look at this. What were we doing? For this one, we were saying, okay, go through the map palette and look at the meta tile. So if they don't match, okay, I mean, we could do the same thing here. Again, not the not the most efficient way to do this, but it'll work, and we can always clean it up. You know, this is not something that's real time, so I'm not super worried about this being the fastest code we can possibly get. I may actually just make this a, well, I don't know that it's worth making a function at this point. Same thing here. So in this situation, what we're doing, okay, and then what we need to do here, ideally, is we want to get, let's see, so, I mean, this is kind of like a condensed version of what we were doing before, where that was doing it for 64, we're doing it just for 8 here, because we're doing it for a single row. So we have that 0. And let's see. Did I have a separate thing for that? I did. So this is attr result, attr index equals, and it's the same thing here, right? Yeah, maybe we can extract this out because it's really just a short form version of this, where we're saying how many metatiles we're dealing, where we need to pass how many metatiles we're dealing with. In this case, we're doing it for 64. In this case, we're doing it for 8, and we have an array of either 8 or 64 that we are handling this with. And then when we're done, we say, okay, write map file attr result, size of attr result, and then that's it. So that'll write our attributes. But like I said, I'm thinking we would probably want to extract this a little bit. So let me copy this here. All right, so get metatile attributes. So let's see. We have this is a char array. Okay. So we have our map buffer. We have our attribute results. We have our max results. And then let's see what else. And then we need our map palette, which tells us which metatiles have what palettes. That should be pointer. Start. We can turn this into that. And this will populate. The only difference is, let's see. We don't need this because that's passed in. And the end is max results. And I need a semicolon. Okay. So that should give us what we need, and then we can just call it this way. We say get metatile attributes, and It's going to need map palette, map buffer, attribute result. The start with is map beginning. The width is map width, and the max results is, we're going to say 56 because it's really 56, even though the attribute result is 64 bytes. What's the problem with this? This is an unsigned char. Oh, okay. Sure. And then this goes away. And then this is the same thing now. You say, yeah, actually we can do that. So we set adder result 0, size of adder result. We'll reuse this even though it's a little too big. It's okay. Map palette, map buffer, result, map. So this is now start location, map width, and this is just 8. And then we get rid of all of that. I'm gonna hold off on writing this because I want to make sure that this is working correctly with these changes. Alright, so what I want to do is I want to just export the project, and let's see if when I do that, really the only thing that will have changed is this. So let's take a look at this and see what happened, if anything. Hopefully nothing noticeably changed and all the colors look correct up until the point that they need to. Yeah, nothing looks out of place, so that's, no, is that right? Yeah, that looks good. Okay, so it looks like it wrote that correctly. Let's take a look here. Right? Or no, that should be the dark blue, so no, it didn't, it messed it up. Okay. So if it messed it up, the question is what did I change that messed it up? So let's hit that breakpoint there. Export. So let's see, that has nothing in it right now. And if I, why is that? And is max results. Attribute is equal to start. Oh. Well, that was dumb. This should be start plus max results. Okay. That looks like it actually did something this time, as opposed to last time where nothing got updated. So let's reload the ROM. Okay. Yeah, okay. That's what it should have looked like. That's the right blue color. Okay, good. Cool. So that's all good. So now let's change. Well, let's see what this is doing when we export again. So this is now 0. Are we getting any updates to this at all? Okay. You can see the AA shifting down, which would correspond to, if we go back to, we have these diagonal meta tiles, so I could understand it shifting the palette accordingly. So that looks promising. Obviously, like I said, it's not writing out the additional data right now because I wanted to make sure that that routine was working properly. So let's add that in now. So now it's going to write the additional 8 bytes per row. And obviously that's going to mess up our NES code because it's going to start reading in data that's not actually relevant to the row. It's going to be reading in data that's related to the attributes, which, let's just confirm that we're kind of seeing things happen like every, what? Segment code F overflows memory area ROM. Oh, okay. Our level is too big. I guess it would be under the circumstances. Where is the configuration here? So I have this configured right now. So ROM 0 is 8K. No, it's only 2K. Let me see something here. Wait, is it 2K? No, it's not 2K. What is that? It's 8K. Okay, I was right. I said 8K, and then I realized I was looking at this and just incorrectly transposing number systems here. So I guess the question, I'm pretty sure that those sizes are based on the mapper's definition of what the ROM sizes are. The problem then becomes eight K, and 16 fixed. 8K RAM, 8K switchable. Eight K, 8K, 8K. So this map is too big. I mean, how many meta tiles do we have? What is this? Height 100. 100 divided by 7, so it's 14 screens high. And I mean, it's not exact, it's a little bit more, but so 98 times 8, 784. Yeah, I guess there's a lot of other stuff that's getting assembled into this, and we're now getting about a K above that 8K limit. So I mean, part of that is I've got everything all in the same 8K ROM. Let me see something here. That's going to be in char RAM. Sorry, I'm kind of thinking through what I've got in all of these areas and what, if anything, I can get rid of or condense. I mean, what we could do just to kind of simplify things is we could reduce. It's not really going to do that much. I was going to say we could reduce the number of meta tiles, but that's not really going to save us all that much. I guess the issue is that the level itself is almost 8K. Which, thinking about this now, that seems like a lot. I mean, obviously it's a problem because we've only got one level that we're working on, this test level, and it's already overflowing our available ROM space for data. Not that we couldn't put it somewhere else, but the point is that it's pretty big, and that's just one level. So let's see here. Now it's only 1K. So adding this added 8K. Oh, okay. Well, yeah. So part of the problem is I'm writing 64 bytes every time for every row. I forgot about that. That's supposed to only be 8. So I meant to change that, and it was writing the 64 bytes of this attribute result array every time for every row. That's obviously way too much data. So now the level 1 file is only 2K. That's better. But you can see that if you're not careful, you can make a mistake and also potentially run out of space pretty quick. Alright, so let's reload this, and now loading should look wrong. It should have every other, yep. So you can see every other set of tiles is right, and it's because now every other meta tile row is actually attribute data and not tile information. So now we have to figure out how we're going to handle updating the attributes properly. And let's start with this. When we load the next tile, let's skip a row to accommodate for the attribute data, just to get this going with that in there. Okay, so process scrolling, increment meta tile subrow, increment meta tile. Okay, so here's where we're actually modifying the meta tile row. Load A, store A, M tile Y. And then load A8, clear carry add. Right, so we are adding 8 to the data there. We basically need to do this twice. Or actually, no, that's dumb. Just add 16. To skip this. So now our level should look good again. And that is right. All right, so that confirms that that data is being loaded properly. All right, so how... I guess I need to kind of think about this a little bit, because I didn't really think about this too much beforehand. So basically we've got 64 bytes for our attributes, and for the first screen we just load the whole thing, and then the next meta tile row, which is going to be above the screen here, right above the viewport of the screen, is actually going to be the attribute table that's down. Well, it's going to be, yeah, it's going to be the one that's down here. But is it going to be... Is it going to be a full row, or is it going to be... Let's take a look, because I don't know if it's going to be the full name table row, or if it's going to be half the name table row. Let's reload this and slow down the emulation and hit start. Okay, so let's see. I think it's a full meta tile row, but I don't remember. Yeah, so what it's doing after the initial screen load is the last two rows are, pause please, the last two rows are being populated because I load 7. Well, no, that wouldn't, let me think. 7 times 4, 28. But it's 32 by, yeah, oh, okay, right, yeah. So I don't load all of the, I'm only loading 8 by 7 meta tiles, so the last two rows are empty, which is fine because the HUD covers that. But then when we're scrolling up, we start by loading a full meta tile row, starting with the bottom. So what we need to do is in the attribute memory, again, because it's kind of divided up, the last row here, and we talked about this a little bit last time, I believe. You have the last row here, which has the meta tile or the attribute configuration, where this is going to be essentially a meta tile now. We need to, well, so this is a meta tile, but the screen attributes are actually like this. Let me use another color to differentiate. So even though the screen looks like it's drawn a whole meta tile, the attribute actually overlaps like this. And so we need to update the bottom left and right, the top left and right of the attribute here, and the bottom left and right of the attribute above that. And that's made even more tricky because once we get, let's see, so that's 2, here's 3, here's 4, here's 5, here's 6, here's 7, and there's 8. So if we continue this sort of pattern, what we're going to see is we're going to see there's another meta tile, there's another meta tile, there's another meta tile, there's yet another, and another, and another. And then we're going to get a partial meta tile here that then draws the bottom half here on the top of the name table and the top half on the bottom of the name table, which then corresponds to sort of a flip in the logic, right? So now we start with the top of the meta tile corresponding to the top of the attribute block, and then the attributes and meta tiles line up. And so what we need to do, a little tricky, but basically what we need to do is half the time we need to update the bottom part of the bottom part of one and the top part of another attribute block, and then the other part of the time we need to just update the whole attribute table. And that's the easier one, right? Because we just have our byte, which has the 4 palette values that we write into it. In this case, we have 2 bytes, and we have to write, let's see if I remember, well, you know what, I think I'm right, but the ordering matters, so let's get that right the first time. PPU Attribute tables, top left, top right, bottom left, bottom right. So the bottom is in the most significant bits and the top is in the least significant bits. So in this case, we have to update these and these, which is kind of a pain. So, and that's the first case we actually have to solve here, because the first screen we're drawing, we've aligned the meta tiles so that they are lined up with the attributes nicely, like this case, which is easy to solve. But because of the way that the screen is laid out with the number of tiles and not being square, we immediately start on this other case as we start loading in more tiles. So let's see. So I'm trying to think. Trying to think how I would do that. Vastarak, you just asked about the configuration for the drawing area. I mentioned this one other time. You can change the way that the drawing gets cropped. If you want, you can have the full number of pixels. The thing that I'm talking about here, though, is not related to that, because the screen being the dimensions that it is, it's 256 by 240. If you do right, it's 32 tiles by 30 tiles. These are 8 pixels by 8 pixels, right? So it's not a matter of the way that the cropping occurred. It's because of the way that the screen dimensions cause the tiles to get drawn on the screen. There's no, because it's not a square screen, you automatically are missing the 2 rows at the bottom by comparison to the horizontal number of columns, right? So because we're using 4x4, we can only fit so many. We can only fit so many 4 by, or they're really 32 by 32 meta tiles, 32 pixels by 32 pixels, right? If you do the division, you get 7, but that's not exactly right, because 7 times 8 is, it's 7 times 2 times 8. No, 7 times 4 times 8. Sorry. Is 224. So you have this gap of 7 times 4 times 8, 224, 240 minus 224. You have this gap of 16, 2 rows anyway, which is exactly 2 rows of it, the 8 by 8 pixels. So this is just an artifact of the way that updating the tiles works on this system, because of the way that we're scrolling. So getting back to the attributes here, what I'm going to have to do is I'm going to have to figure out, let's see, so the layout is, well, it's an array of 64, 64 bytes. And I want something that's going to point to the next row of attributes I need to update. So I think what I want to do is I want to create something called ATTRMem. And once we load the level, what I want to do is I want to load a, let's see, so if, well, we know, okay, the attribute memory is at 23C0 for the screen, and if we, and that's 23C0 because we're saying we're at 2000 and 960 is 3C0. So I want to, for the first row, I want to start at, or sorry, for the first row that we're updating dynamically on the screen, I want to start at essentially the bottom. We're going to start at the bottom row of the screen, like we were seeing when we restarted the emulation. Here, we'll do it one more time just to confirm that I actually saw that right. Yeah, so you can see here, if I wish you could zoom in on the name table, but you can see on the name table that the bottom two rows have no tiles in them, and that's because we've drawn 7 metatile rows here, which is exactly right, because now as we scroll this up, the top is truncated by the way that the NES renders with, you know, the overscan, or not the overscan, just the way that the CRT is normally going to truncate the tiles. And most emulators do that truncation, and if you remember, if we turn that off, we see the tile updates happening on the top. So this is all good. So basically what we want to do is we want to say, okay, if we know that the memory is at 23C0, what I want to do is I want to subtract 8 bytes from 1024, which is the entire memory for the name table, tiles and attributes included, and that gives me 3F8. And so my attribute memory is going to have, let's see, 2, 3, and F8. Store a attribute ATTRMem, yeah, and basically all I'm doing is after we're done loading the level, we're setting ourselves up to start at the appropriate attribute to load the attributes correctly. So set up ATTRMem to be correct for the next row of metatile info we are loading. There's a rub there that I just thought of, but I'm not going to get into it yet because it's easier to see when it occurs. So let's just leave that for now. So that's good. That is the appropriate location. And then, let's see, now that we've got that, we need to know if we are in a mode where we are updating the attribute in one write or if we're manipulating the attribute by only writing. Now that's actually, how would we do that? Because we can't read that from the PPU memory. So we would need to know in order to know what we're updating it with, when we do these updates of the nibble versus the entire byte, we need to know what the other half is, because we don't know what it was necessarily, since we can't read it and manipulate. Like normally, if it were just normal memory, what we would do, right, is we would load it into A, and then we would take bitwise AND it to clear out the lower nibble or the upper nibble, right, the 4 bits, and then do a bitwise OR to concatenate the two 4-bit values properly after shifting if we needed to. But because we don't know what the original value is, then we can't do that. So I'm wondering, it may have to, in the attribute, in the tool here, we may have to make it be smarter about what it writes out so that it handles all of that. And basically what it would do is it would say, okay, depending on what is being updated, I either have to write, oh, that's kind of gross. That means that for some rows you have to write 2 rows of attribute, or for some part of the time you have to write 2 rows of attributes at a time for every row you update, and some part of the time you have to write only 1 row of attributes. No, I don't like that. Am I going to have to keep an array? Am I going to have to keep memory of what all the attribute values are so I can just update it in RAM properly and then update the attribute table? I feel like that's what I'm going to have to do. So the problem is that if I don't know what the value is, right? I was saying, okay, well maybe the tool can figure it out and write it. And then while it can, problem is that then you have to write, okay, because depending on the mode that you're working on, if you're working on where you have to update the 2 bytes, the 2 bytes are not contiguous bytes, right? So they're not this byte and this byte here. It's actually like this byte and that byte, because for each one you have 7 bytes in between, which means that you have to realistically write both rows in order to kind of get a general algorithm that would allow you to handle writing the 4 bits of those bytes across both rows. But that's really ugly. That's not going to work very well. Because, I mean, it's going to require storing all of that data in the map, which we don't really want to do because it's going to take up a lot more space. But also, then the tool has to know how you're starting your writes to the name table right? So if you're starting your writes the name table where your initial meta tiles align correctly, then it wouldn't need to know that it's then going to write the sets of 2 attribute rows for the first set of 7 rows or 8 rows, and then alternate back and forth. And I don't know that I want to encode that knowledge into the way that the asset tool works, just because then if we change that for some reason, then that breaks the asset tool. We're not going to get away with the requirement to update the attributes twice, because updating the attributes twice is required, right? We can't just write 4 bits to this first byte and then just the 4 bits to the second byte. We have to update each byte completely. And so what we need to have is, I think what we need to have is we need to have in RAM the value of the attributes. So an 8 by 7, or well, it's 8 by 8 really for practical purposes. We need to have a 64 byte array that we would use for storing the attribute memory, so that when we move forward, we can recompute the merged attribute values and then do the writes to memory accordingly. And depending on the mode, we either write 2 rows of attributes or 1 row of attributes. I think that's going to work. It's not pretty, but I think that's how it's going to have to be given the way that all of this works. So in this case, we subtracted 8 from 1024 to get our starting point. We actually need to subtract 16 because we're already in the mode for the first row that we're writing of being in that split scenario of writing 2 rows of attributes. So the offset is 3F0 from the base name table. And then what we need to do is we need to load A, we'll call it mode 1, store A attribute mode. Well, I'll actually give it a real name so that I don't get confused and forget what 1 and 0 stand for in this scenario. So we'll call it split atter mode split. I think you have to have a, let me see if I've got some code here that use that. Yeah. All right. So okay, that's fine. And then where's adder mode? I created adder mode there, and this is adder buffer. Ugh, 64 bytes. Okay. And so let's do this. Load level. So where is that code that's loading the attributes? Because what we need to do is we need to load that into our adder buffer too, not just into the attribute memory. So let's see. So that is going to do that for 64. So this works out perfectly. What we can do is we can say load A there, store A into adder buffer. Can I do it that way? I think you can just do that as an index. Right? You can just use Y as a standard index like that. slightly slower to do that. But then, if I transfer it to Y, let's see. So this is one cycle, one lengthened cycle longer. But if I have to transfer Y to you can't, right? You can do transfer A to, what is this? T, that's the stack. Transfer A to X, transfer A to Y, transfer stack, transfer X to A, X to stack, Y to A. So we could flip some things around or push Y onto the stack and pop it or pull it off. But it would end up being more cycles to do that than just simply use that. So that's what we'll do. So here we're going to just store A into both the attribute buffer and into 2007, which is our video, our PPU register. Let me create the scope. So this, the only real difference that we should see with this is nothing. I mean, it should work exactly the same. And it does. The only difference we're going to see now is in the memory. If we look, we should see some data, 64 bytes worth of data being loaded in at some location here. And we have it towards the end. Let's see. So that's going to be, there's going to be the address for 23F0 is the address for the attribute that we need to update next. So let's look for that here, 23F0. So there's 23F0, and then this is all attribute memory for 64 bytes, which is what, 40 hex? So that's our attribute memory loaded in from the map currently. Let's restart here. Seems odd that it's got some values in there. Oh, you know what? I'm off by a little bit, I think, in my because attribute mode comes after the memory. So this is the mode. So this is actually going to be 4. Where's 40? So this is 40. So this has that attribute loaded. It's weird that's only got the, would have thought would have had more of those values. Let's take a look here. Attribute buffer. Y is load Y 38. Oh crap. This should be X. Well, that's good. X is what I wanted to use anyway, so it'll be, because it's more efficient. So that's good. There we go. That looks more like what I was expecting. It's because Y was offset by this value of 38. Which is fine. I mean, that's what we needed it to be for reading the memory from the level file, but the X needed we needed to also write into the attribute buffer starting at index 0. So that's fine. And now what we need to do is, like I was saying, so now for the next set of values, so if we go and look at memory in the PPU, if we go to 23C0, we should see the same values essentially. 23C0, and again, it looks pretty close to what we were seeing if we. So that's that. If we go back to NES memory, our NES memory is this, and if we select 40 bytes, 40 hex bytes, we've got the same values, which is good. And then we could even where is that? 8. Oh, I had that right. So if we break this down, these are hex bytes, so it's, I need to have both. More adventures in me messing with text editors. Though the reason I want to do this is because I want to show how the attributes correspond to the meta tiles. Right, so here's our 8x8. You can see the values where we have A correspond to this portion of the screen where the palette is different. So what we need to do now is we need to say, okay, we're loading the next row, and the next row is part of a meta tile that needs a certain palette, and that certain palette needs to be loaded into this attribute. And let's see, yeah, so it needs to be loaded into this attribute and this attribute set, because this attribute set controls the tiles, the half of the tiles we're going to see, and this is going to control the other half of the tiles we're going to see. And so we need to manipulate in the on the top part of the attribute, we need to manipulate the upper 4 bits here, which are is the first digit in the hex value, and then in the bottom one we need to do the lower 4 bits, which is the second digit here in that hex value. So let's do that. Actually, we don't need to even touch the top attribute yet, right? Because, let me see. This is all... let me go here for a second here. That's going to be one meta tile. It's going to be the last row, but it's just going to be where the hell is that page? Is that considered the top or the bottom? It's considered the top, so it's going to be the bottom, or it's going to be the second digit in the hex, the lower, or the lower significant, least significant 4 bits. And that's all we need to manipulate on that one. And then the next one, we need to do the upper, and then right, the upper of the next. Let me think about that. So we'd start with this, right? And then the next set of tiles that we wrote, we wouldn't have to do anything because that would be okay, because that would be the 16 still. .32 by 32 pixel, 4 by 4. Sorry, I'm trying to figure this out here. So this would be this, and then, or yeah, so this would be this, right? We would be updating. And then the next one we would be updating is this one. So we would be doing this one like this, and then the next part we would need to update is that. And then same thing, and then we'll do different letters here. And then so we actually, in that case, we're not doing 2 rows at the same time. We're doing 2 rows, the same row twice, versus just the 1 row completely. Okay, so let's go back to our code. And so what we're doing is in split mode, we're going to count how many times we need to know. We need to update the same row twice, essentially. And then in single mode, we just do 1 row at a time. So let's do this. So kind of pointless to have all of these. At some point we're going to consolidate some of these things, I think, so that we're not consuming so much memory on stuff like this, but this is okay. We're not really using that much memory. I know we only have 2K, but we're not really using that much. That 64 byte array is the biggest thing we're using right now. All right, so we have our counter, which we're going to use just to make sure that we're depending on the mode we're in, we're updating the attribute buffer properly. And then we have something we'll call attribute row, which corresponds to the row that we're in here in attribute buffer, so we don't have to keep recalculating that. save ourselves some cycles here. So the mode is split mode. We've got the right attribute memory there, and then the location in the attribute buffer, like I was saying, is going to be the 1024 minus 8, 16. So 3F0. Oh, wait a minute. No, dummy. It's 64 bytes. How many metatiles is that? That's let's see. So it's the first row is 64 bytes is it's 57. So we don't care about the last two rows at all. So that's 16 from there, right? That's 64 minus 16. No, that's because 7 times 8 is 56, and then okay. So right. Sorry, because it's the 4x4. So the first row is at that 56 marker, right? It's at that 56 marker because that's the last 0. Let me think about that. So 56. That would be the last full metatile. Yeah. So what is 56? That's 38 in hex. No, not attribute counter. What do they call it? Attribute row. So that's the row that we're going to be looking at to get the bytes that we need to manipulate depending on the mode that we're in for the way we're updating the attributes. And attribute stored into attribute counter. Okay. Set up attribute mode to be split update. Then let's see. Set up attribute row to indicate which buffer row to start at, and initialize the counter. Okay, so now let's go to our code here that we're using for all of this lovely business. So okay, so this is all of the updates for the actual tiles. And now we need to handle the attribute. I don't want to do it there. I want to do it when we know that we actually need to load a new row. So here. So what we need to do is compare, well, load A. Load a, what is it, attribute mode, compare to split branch if not equal to attribute update attribute no split to update attributes split update attributes no split attributes done. Okay, so we've got that. All right, so if it's split, what we need to do is we need to look at the counter, load a attribute counter, compare it to 1, branch if not equal, which would mean that it's 0. So we haven't loaded the attributes yet. So we wouldn't need to increment the or decrement the memory or anything yet. Let's do this, the first case. Let's just actually, we can do this, right? So say branch if we load A with a value of 0, it's going to be, say that it's equal, otherwise branch if not equal. So if we load A with attribute counter, if it's not equal, we're going to go to load attributes and decrement. So load attributes and decrement. Otherwise, we're in load attributes. Inc count. We'll call it load attributes inc counter, right? So we're going to inc add or counter. And if we are loading the attribute and incrementing the counter, that means we are updating first the most significant 4 bits, and then after that we do the least significant 4 bits. So what we need to do, let's see, so we need to, let's add some comments in here while we're doing this so that I remember what it is I'm doing when I have to come back and revisit this. Check the attribute mode to see if we're splitting the attribute data at this time. Split update mode. Check the counter to see if we've already updated this set of attributes once. If this branches, we've updated the most significant bits and need to decrement the address in PPU memory for the next update. Otherwise, we're okay. No, we've got that covered. Okay, so this is update and decrement PD pointer. So in this case, we're just doing a simple update. So what we need to do is we need to say update. I always forget which one this is. MSB bits. So let's just update the most significant byte bits, or most significant bit. Most significant bits. Update the most significant bits with the palette information. So there are a few things we got to do here. Oh Lord. So first we need to know what those values are. And then we have to load them in. So, I don't know if I'm going to finish this tonight. Let's see if we can do it. So basically right now what we're doing is we're skipping over the attribute info that's being written out here. So the first thing we're doing is we're writing out the we're writing out the map row, and then we have the attribute information. Every time we increment, we're skipping that right now by adding 16 instead of 8. And the reason that's okay is because we don't care about that. But what we can do is, let's see. I mean, we do care about it because what we need to do is we need to load that from row mem here. Why is store row mems? This is actually calculating the offsets. Oh goodness. I almost wonder if it's easier not to have this interleaved into the loading it into the map data like this is fine because the process is essentially the same. Just thinking what makes more sense, if I should have it write the attribute memory first in the asset tool, and then I guess so, because we probably want to load the attribute memory first. Well, crap. I mean, the thing that I'm kind of humming and hawing over right now is that essentially this code here that we have for loading the meta tiles. At least to the point where we get the row mem position. I mean, because we're not, it's not like the actual meta tiles where we're splitting, you know, so these meta tiles are actually, you know, the 32 pixel by 32 pixel. So it's 4 by 4 tiles. So when we're scrolling, what we're really kind of doing is, I mean, we're cheating. We're not keeping real counters into the absolute position in the map, right? What we're doing is we're counting how many pixels we've scrolled, and if we hit 8 pixels, we then say, okay, we know we need to load the next row in the meta tile, so we go look at our position in the map based on the meta tiles, and then based on that, we look into the meta tile itself and load 4 tiles at a time the next row, and that works just fine. For the attributes, we have one for each of these meta tiles, but it's encoded into the same location. And what I was originally doing here was kind of trying to make this happen outside of the map updates, but I'm wondering if it's going to be easier code. I wonder if the code will be less gnarly if we can do something where we can sort of piggyback off of the code here that is getting the meta tile info. Because this is incrementing y to get the meta tile that then needs to be used to offset into the actual 8 by 8 pixel tile that needs to be loaded into the PPU memory for the name table. So we just count 8. We count one row off, and that loads up the 32 tiles quite nicely. If we interleave the attribute memory values here within the meta tiles, then we can, depending on the mode, do our updates with the appropriate values. I guess I got to think about that. That's annoying because I was really hoping to get that working tonight, but just to kind of flesh that out a little bit. So right now we're writing one row at a time, a row of meta tiles and a row, right? We have a row of meta tiles and then a row of attribute data. And what I'm realizing is that basically the code to look this stuff up as we're scrolling is going to be essentially the same. And I don't want to have to reinvent the wheel here, and so I'm almost wondering if it makes more sense to just double the number of elements that I'm incrementing and say it's meta tile / attribute data, and we're just going to alternate. So meta tile attribute, meta tile attribute, meta tile attribute, like that. And so this would be 16 instead of 8, and that would effectively be, that'd be much better, because then we can incorporate the attribute loading stuff into the tile loading stuff, and then we don't have to do any sort of separate lookups and stuff like that. I think that's what I'm going to do. So it's annoying because now what we have to do is interleave the data here instead of writing two separate. And it's not that hard. So we do something like interleaved. And you say I is equal to I less than 8. Yeah. I can't use I. Basically what I'm going to do is say interleaved interleave is equal to map buffer start location plus interleave, right? So interleaved is equal to that. Start location plus interleave, except that this is going to be divided in half because the map buffer is only going to be a width of 8. And then we'll do the same thing. We don't need to increment this here then. And this is this will go here. I should do this too anyway. And then what we'll write is so yeah, again, so what it's doing is it's writing the interleaved. It's saying, okay, from 0 to 16, I'm going to write a map value, and then I'm going to increment it and write an attribute value. And each time I'm taking the start location, although this should just be this, I'm taking the location, whatever the start location is, in this case it's 0, and then I'm adding to it the interleave value divided in half, which is fine because it's going to, if it's going to then essentially increment these guys linearly by 1, but this is going to increment by 2 each time. So what we should see is that this will work correctly. Export. So interleaved has 2 values, right? The value, well, the value isn't 2 yet, but it will be. I want to see one of those attribute values get written sometime here, possibly. You know, we may not because of just the way the palettes work. So let's do this. Let's just kind of see what this looks like as we go. Okay, so yeah, that makes sense. Metatel 2 will have that attribute data. Okay. So obviously that breaks the way that the tile info is loaded, but hopefully that means we can be a little bit smarter about how we traverse and load the attributes into memory. Here's the assembly code. So if we just build that and reload it, it's going to be broken, but I just want to make sure that it's broken in the way that I expect to see it broken. And it is. Everything is kind of spaced out. Good. Okay. So now the next thing we need to do is we need to fix this code so that it handles this properly. So that needs to compare it to 16 so that we're incrementing by the right amount. And then let's just, to fix this, let's increment by 2 each time. So it will essentially fix the stuff that was broken, but we don't get anything for it yet. Yep. Cool. So that's good. That's now looking correct. So now what we need to do is we need to do the following. Y will give us, once we increment it, the attribute information for that meta tile. So what we should be able to do is we should be able to say load A, row mem, Y. This is the attribute value for the row we just loaded. Except, I guess we only want to do this update when we've hit the boundary of the meta tile and we've switched to a new meta tile. Which we handle over here, increment meta tile row. And that's because we're just counting the rows within the meta tile here. So we wouldn't even have to do that. Well, so that's problematic because now we're essentially forcing ourselves to skip the meta tile attribute information every time we load another row. I guess that's not that big a deal. We can always have something, a flag that tells it not to rewrite the attribute data every time if we find that that's taking too many cycles. Okay, so I wonder how slow it would be if we rewrote the meta tile attributes every time. I mean, you're talking about 64 updates. So that's 64 stores into absolute stores. So, well, yeah, that could potentially be pretty slow. Right, so 128, 256 cycles. Could be upwards of 256 cycles to do that. All right. Well, let's subtract with carry, not store. It's even more because it's 5 cycles per store. So 64 times 5, we're getting 320 cycles. Yeah, all right. We don't want to do that. I mean, to that point, we probably don't want to keep restoring the attribute data, but that's, like I said, we can set a flag for that. That we would only do it if we hit a new meta tile row. But let's get that working, I guess, for now. All right. So this is the attribute value for the row we just loaded. This is all right. I'm just gonna make this work, and then we can add in that flag, because the more I think about it, the more it irks me that we're gonna keep rewriting those attribute values. So let me think about this. If we're in split mode, then we need to update just the lower 4 bits of what's in the attribute memory and rewrite those bytes. The problem is with this update, yeah, you know what? We actually have to do it this way, otherwise we end up having to count the number of rows we've loaded in to make sure that we're updating the right attribute bytes and the right number of them. So all right, let's get this working first, assuming that we're going to do it, and then we can update the code that skips it, or add the code that skips it, I should say. How we're going to do this? So we have our attribute buffer, we have our attribute row, and we know what the mode is. We have the value, but that's just the row. So the byte that we want to let me do this. Instead of calling it attribute row, let's call this attribute index. The reason I want to call it attribute index is because I want to be able to just increment this for each attribute we're updating. So load load A attribute mode, compare it with split branch if not equal to set attribute no split. This is set attribute split. Done with attributes. So, all right, so we know which mode we're in. This is the split mode, which means that we need to now load A with the attribute counter, right? That's what I called it. Branch if equal to if it's 0, we want to do the least significant bits. So update update LSBs. This is update MSBs. Update LSBs. So if the attribute counter is 0, we're going to update the least significant bits with the new attribute value. So we are going to load the attribute value into A, and then we need to, well, even before that, I guess what we need to do is we need to load A with what is it called? It's called attribute buffer Y, and so we need to push transfer A to Y and push A, because what we need to do is we need to load Y with attribute index, and then we want to, actually we can do this with X because, right, we don't care about the value of X anymore over here. Transfer A to X, yeah, we don't care. Okay, never mind, sorry, we don't need to use Y here. Load X with attribute index, because this isn't a pointer that we're using. This is a it's just a buffer. So we're loading the attribute value here, and then what we want to do is we want to AND A with F0. So we want to get rid of the least significant bits. We want to then let's see, how do we do, can we do, that's not what I wanted. As much as I like open table, that's not pertinent to the discussion. Okay, we can do this. So what I want to do is then I want to do an aura, an OR A. So I want to take the value of the attribute and just OR it to A, knowing that it's going to be only 0 through 4, so we don't have to worry about it modifying the upper, the most significant bits. And then once we have that, so there's another thing I hadn't thought of, which is that right now we set up 2006 for the tiles, and in order to update the attribute memory, we have to also use 2006 to set the address, which means that we are messing with the address here that's being used there, which is not going to work. Let's store this back into attribute buffer X. So that's our new value. And I think I'm going to end it for tonight, because there's just kind of it. Every time I try to make it simpler, it keeps kind of unraveling. And not that we can't get it done tonight, but I didn't want this to be a 4-hour stream, and I feel like we could easily probably spend another couple hours on this. Vashtaraku sent me a link to look at an image. What is it? Yeah. So here we can all look at this. So yes, there is a setting in the emulator that changes the cropping. If we change it here to this, what you see is there's going to be some artifacting. If you go to the name tables, nothing has changed in the name tables. So what you sent me is a link that shows how the emulators draw the screen in terms of cropping and the way that old CRTs worked. So most emulators crop the screen pretty heavily, because old TVs effectively did that as well. So if we go to NESDev here for a second, let's go to the PPU. I believe there was something where they're showing this. Okay. And what you can see here is, if you look at this image that was put together, the Nintendo is always generating 256 by 240 pixels, right? But what the emulators do is they're simulating what old TVs used to do, which is that they generally didn't draw this first 8 pixels, and they generally didn't draw the secondary set of 8 pixels. And then it was kind of questionable about these pixels here, like, the ones on the border there, most of the time those were drawn on a decent TV. Not every TV, but decent TVs. And if you wanted to guarantee that it fit on a TV, you want it to be within this blue zone, right? And so I've seen it called, action safe area or the safe area, all what they're referring to here, all these terms. But that doesn't change the fundamental issue that we're dealing with in the way that the tiles are being drawn for this game. And the fundamental issue we're dealing with is that our meta tiles are 32 by 32. And so on a 256 pixel horizontal display, we get 8 full meta tiles going across, and you can see that here. 1, 2, 3, 4, 5, 6, 7, 8 fit perfectly. But on the horizontal, right? On the vertical, the number of rows, when you do, if we change out of programmer mode here, if you take the 240 pixels and divide it by 32, you get 7.5, right? And all that means is that we get 7 full rows of meta tiles, and then there's a half row of meta tile, which incidentally computes to 16 pixels. And that's fine as long as we take that into account. The problem then becomes that as you scroll, because we're updating row by row, when we restart the emulator, you can see it here when I've turned this drawing on. You can see that there's a row above that's empty essentially, and there's this row that was just drawn here, right? And that row corresponds to, it's actually the bottom of the screen. It's the bottom 2 rows that we didn't do any drawing on because our meta tiles don't fit properly. Now we could have made our meta tiles 16 by 16, but then we run into other issues with the way that the attributes get updated, where it's much more, there's even more manipulation that we're going to have to do with the attribute, bits in order to make that fit properly. The most we have to do right now with the attributes is we have to kind of split them half and half. If we were doing scrolling horizontally, I mean, it would be super easy, because as we scrolled over to the right, the meta tile would roll over to the next meta tile, and we just update the attribute. And you'd see that artifact that you've, I'm sure, seen in a lot of Nintendo games, where the colors on the left-hand side would be wrong, potentially depending on what we've loaded, but they'd be right on the right-hand side. And then if you flipped it when you were heading left, you'd see the same thing on the right. And that's because our meta tiles would fit, sort of one for one with the attribute table that's here, because we're using the same size. So right now what we're fighting is the fact that on our first update to the name table, we have to update this attribute row of the half meta tile essentially. So we have to update this one and this one. And then the next one we have to do is this one. Well, actually, let me think about that. So we have to update this. Well, maybe we only have to... Oh, that's what it is. We have to update this twice, because we have to update it half for the first row and then half for the second row. And then the next time we have to do half for the first row, half for the second row, and then half for the first row, half for the second row, and we have to keep doing that split update because our meta tiles are actually, to start off with, they're taking up, they're crossing these two, they're across these two attribute rows. Once we complete doing that, when we're done with that process, what's going to end up happening is we're going to get to this point where we do this update twice, and then we're going to have a point where the meta tiles actually overlap properly, and we'll just be able to do the single byte upload or update, I should say. I think if I'm thinking about that the right way, but that's why I want to stop now, because we've been doing this for over 2 hours now, and I want to think about this for a little bit and make sure that I don't screw this up, that I'm not overcomplicating it or missing something else, because we're at a point where getting at the data isn't that big a deal, but we have to figure out how to properly update the memory. While we simplify the process of retrieving the attribute data, now the process of updating the memory for the attributes is more complicated. What I might end up having to do is I might end up having to write this information to an 8-byte buffer that then gets written out once we're done updating these meta tile, updating the row using the meta tiles. So I'm not 100% sure. I got to think about it a little bit and kind of work through this, because obviously it's a little complicated and it's easy to screw up. So hopefully that explanation helped. If you have any other questions, feel free to message me on Twitter, and that's not just for Vash Dirac, that's anybody who's watching. I'm on Twitter at Clairvis. I'm on the Nintendo Age forums and the Discord, and of course you can always post a comment on the video on YouTube, and I try to get back to everybody pretty quickly. So have a good night. See you Thursday. Sorry for the like I said, the long time between streams, but should be back to normal here, and we'll be able to hopefully get this working properly on Thursday. Okay, so have a good night. Thanks for watching. See you next time.